Hey YouTube, I'm back with you in the shop today because I've got a new invention coming for you guys. Over here, you can see I made a little handle for it, just in case anybody doesn't have any power tools and they want to be able to play with the thing. But what I made over here is this little thing. This is a little electrostatic generator that you guys could build for yourself at home. Right now I got the top taken off of it. But I'm going to put this up in a link in the video to where you can pick up the designs. I'm going to sell them for a modest price just because I am trying to make this my day job. But the machine is pretty impressive for what it is compared to this thing over here. This little thing over here is, hey, it's a fraction of the size, and okay, it's a fraction of the power, but it's a bigger fraction of the power than it is a fraction of the size. So I'll show you what kind of current measurement we can get out of this machine here. So the way that I've decided to measure current now is I've decided that I am just going to use a 20 kV spark gap with a capacitor bank. And I'm just going to measure the frequency of charging of the capacitor bank and just use the average current from the capacitor that it would take to charge that capacitor bank. I know that the real current flow will be larger because capacitors act as variable resistors through their charge cycle. So that does affect what the average current flow will be. But the fact that they're acting as a variable resistor, that also means that they kind of simulate a load a little bit. So this is probably actually a really good way to measure the output that the machine is capable of. Now, I used to have 20. Mind you, I could only fit like another 7 or 8 in this lineup here between the boards. The reason I know that this spark gap is 20 kilovolts, or is a minimum of 20 kilovolts, is because I've destroyed this entire batch of capacitors over here by overvolting them. So this spark gap is just close enough that it's not going to overvolt these capacitors and destroy them. All right, so I'm spinning it with the skill drill here. It goes up to 2,700 RPM on the out. You can see here the motor inside goes up to 43,000 RPM, so it makes a bit of a whine while it runs. But I'm gonna get this to spark, and then I'll let it spark again, and then I'll let it spark again, so that you guys can see the time frame between two fresh sparks. You can see the machine's getting started. So there we go. There's the two sparks. And you can sort of see in here, but I have an inductor there. And then this piece over here, this whole thing was designed to be modular so that the pieces and fixable. So these pieces slide in and out. They have plates on both sides of the pieces so that both plates act on the central disc for the purposes of induction. And what this means is that this machine here, volt for volt, has twice as much induction on each sector that's on the disk as compared to this machine over here. Volt for volt, it has like, and on top of it, because it's a pipe, volt for volt, it has like a quarter of the induction per surface area. So this machine over here, even though it's producing, it's significantly smaller and has a significantly smaller rotor, based on the timing over there, when I calculated it earlier, I counted 1 spark in every 6.8 seconds, and that's a 9 nanofarad capacitor bank. So that charges 1.32 nanofarads of capacitors to 20,000 volts once every 6.8 seconds, which works out to an average current flow around around 24 microamps per second of current production. It's pretty friggin' awesome for something like as small as this. This big machine produces more. Instead of 6.8 seconds, it produces a spark roughly like once every 1.8 seconds. I'd have to put it back on. You can see here the little protection came off of the foil over here, so I got to tape it down again because I'm having corona discharge losses on it now. But I'm going to go to the computer and I'm going to show you actually before I go to the computer. So to show you the discs that are inside of the machine, I purchased Sparkit discs, but because I want to sell this, I knew that I was going to have to make something so that people can make their own discs. So over here I've got a disc template that could be cut out, and it's got a little template here for cutting out the foil tape sectors, and I put little insets so that the foil tape sectors could be you'd be able to place them accurately, and at the same time, by having this little groove here, if the disc happens to spin backwards, because the edge of the tape will be kind of inside of this little groove, it makes it less likely that you're going to damage your sectors if they happen to spin backwards. So I'll go to the computer and I'll show you the 3D design files so that you guys can see how this machine is actually put together. Okay, so I'm back here now to show you what the inside of that machine looks like downstairs. Now, this little handle here, it's okay. I mean, it'll do you in a pinch if you don't have a drill or a different motor to attach onto the drive shaft and spin it, but it's not the best. You kind of want speed with these machines a little bit, at least a little bit, a couple hundred RPM reliably and consistently is preferable. So this handle, obviously, you don't need that to be seen. There's a case that fits on the side here and a top cover. Now on the inside over here, this is to hold in the bearings that would fit on the top cover. Ooh, I'm gonna undo the way I hid that. So here we have the bearing cap, and inside of here fits a 26mm bearing. Now the fitting on the inside is designed to fit a 10mm diameter shaft. So this is a 26mm outer diameter bearing with a designed to fit a 10mm shaft. That's what you want here. Now we'll hide the end plate now. And over here you can see underneath we have a bunch of different screw sections here. This is so that you can print more of these middle sections, and you can bolt them together with additional screws. And these additional screws here, I'm just going to make sure that there is enough clearance there. Yeah. Now, these additional screws, they don't need to be in the base design if you just have one. But as soon as you start sandwiching plates, it's as easy to put them together as that. Over here, this piece here, this is a template so that if you want an exact cutout for your neutralizer to be placed, then you would have it through here. This is a template for the shape over here, so you can cut out that shape nice and easy. And then inside of here, you have holes. And this is so that you can bring a brush contact from the plate over to the other side over there. And an additional thing that would be that is done is I run another piece of foil tape down to this edge over here. And I'll explain why later. And then I do the same thing on this side. I run another piece of foil tape up to the edge over here, and I wrap it around. Now, we'll take off that plate now. I call this we'll take off the top cover. This normally seals it up, so that way if you had bearings and you were motivated and you had silicone, you could actually turn this into a sealed design. But otherwise, it kind of holds the plates in place a little bit and makes things a little bit nicer. Now we'll hide this top cover, and on the back you can see it's kind of a mirror, and it's got plates here, but you can see there's no hole going through to interact with the plate here because there's no sectors. So because there's no sectors, it wouldn't make any sense. So instead what I did is up over here where I ran the tape going down, on the sidewall over here, I created a bus bar. And so now the bus bar runs down the length over here so that I can now connect this with another piece of foil tape running up to the bus bar over here. Likewise, for the outputs, I make a bus bar with using foil tape that wraps around the outside over here with this little screw hole so that I can screw down a wire or something else around a post. Now we'll hide this back plate, and we'll actually hide the outer case now. Actually, no, we'll just hide this disc. So now on this side, what I did is I took a bit of foil tape and I wrapped it around coming out over here, and another bit of foil tape, and I wrapped it around coming out over here. And then I folded foil tape so that it was sticking to itself, and then left a little bit on the end so that I could stick it to the surface over here. I stuck one piece over here, one piece as a brush over here, and one piece as a brush over here, with the brush over here being neutralizer, which is what the neutralizer template is for. You then connect the neutralizers using the neutralizer template, which I will move so that it's more visible over on this side. Like that. Now, over here, the output goes to the output bus. Over here at the side, same thing. There'd be another piece of folded foil tape over here. It's stuck to the surface, going to the output bus over here via a foil tape channel. And this over here is the template for your neutralizer bus. or your neutralizer foil tape channel. So the maximum voltage that the machine can possibly produce is basically going to be the short circuit distance from here to here, and then the short circuit distance from here to here, approximately. You have to factor in that the sectors are conductive and they're separated by about it's like 5.6, 5.8 millimeters of space, and there's 24 of them. So in this spacing over here, there is 6 sectors. So that also factors into how the maximum voltage works. Now, once we get past this part here, and you've got your brushes on, then you can just slide these pieces in and out as you please. I have them oriented this way. You really should flip them 90 or 180 degrees. That way you can take them in and out without removing the drive shaft or the bearings or anything like that, or the end plates. Alright, so let's get rid of this piece over here. Now we'll bring the disc back to visibility so that you can just make your own without having to use the Sparkit kit. I decided, you know what? I'll provide my own design. Now this one over here, instead of using Sparkit's 24 sectors, it uses 30 sectors, and so your maximum distance is going to be 2.48 times, so that's 1, 2, 3, 4, 5, 6, 7. And then, so to short circuit from one to the other, it has to do that jump. And then also it would have to do a jump from here going up to there. The other option would be, of course, to jump just straight from here to there. And that has its own distance requirements as well, because it would require jumping to the drive shaft, so 24.82, and then jumping from the drive shaft to there, another 24.82. That's probably the shortest distance, so that's probably where it would go. Now, this disc over here, you just print it off. It's not a thick disc. It is only 1 millimeter thick. Not going to take very much plastic. This depression here is just 1 layer thick at 0.2 millimeters. Did it that way so that it would be obvious as to how to place the sectors, and it would be very symmetric. This piece over here, we'll remove the disc so we can see what I'm talking about. This piece over here is the only special piece you're going to need to print. It's going to be, and the reason I say special is because it needs to be made out of TPU. It's flexible and it's made a little bit bigger around than the opening of the disc on this side, and a little bit tight for the shaft on this side. And that way, when the disc is sitting on it, it grips the disc on the shaft, and it doesn't. The disc doesn't want to move back and forth on the shaft, and it'll spin when you spin the shaft. And so when you're all finished, on this side, you'll have a bus bar going made out of foil tape here and here. And then on the other side, you'll have a bus bar made with foil tape going here and here and up around. So that's that.